one more example with terminal speed. So anytime you see the term terminal speed, you need to recognize that you have to account for drag. What we mean by terminal speed is the acceleration of the object is 0. So terminal speed, by definition, no acceleration. But again, we can only reach terminal speed if there is drag or air resistance. So we have a skier going down a slope. This skier traveling down the slope is experiencing drag and friction. We are modeling the skier as a rectangle, which is pretty silly, but we have to be able to have some sort of idea of cross-sectional area in order to account for drag. So our free body diagram. This skier, of course, is experiencing the pull of gravity. There's a normal force because of the surface. There is some kinetic friction because the skier is sliding down the slope. The problem doesn't specifically state it's kinetic, but it is implied since the skier is actually sliding. There's going to be drag. Drag is always opposite the motion, just like kinetic friction is. So that accounts for everything, all the forces that the skier would be experiencing. We know the angle of the slope, we know the mass. So the mass is 75 kilograms, the angle 17 degrees. This 0.12 would represent our coefficient of kinetic friction. We're saying if this skier is skiing at us, we're seeing the skier with a width of 0.75 and a height of 1.68, the drag coefficient of 1.2. And again, terminal speed is reached when the acceleration is 0. The skier will not speed up anymore. We are, of course, also assuming that this slope is long enough for the skier to reach this terminal speed. Funnily, we had an adjunct professor a number of years ago that liked to do what he called gravity testing, and he actually would reach a terminal speed. He would see how fast he could get going. That's beyond my bravery levels. Now, because this problem is on a slope, the person's on a slope, I'm going to rotate the coordinate system. One nice thing about that is it makes it so the gravity is the only force that has both x and y components. The incline angle is always the angle between mg and the new y-axis. So this side will be mg sine theta because we are opposite the angle. This side will be mg cosine theta because we're adjacent to the angle. We are wanting to get to terminal speed, which will be within the drag. We know terminal speed occurs when there is no acceleration. So we can say that the net force in both the x direction and the y direction is 0. The y direction, partly just because of rotating the coordinate system, the skier is not going to have an acceleration in that direction anyway. And then the x direction because of this terminal speed. So let's write out the net force to set it equal to 0, or we can just say we need to balance the forces because acceleration is 0. In the x direction, we have this component of gravity pointing down the incline or slope. So mg sine theta points down the incline. Because the acceleration is 0, when we've reached a terminal speed, we can say that component of the force of gravity needs to equal the drag force plus the kinetic friction force. That's balancing them out. We could totally say mg sine theta minus drag minus friction equals 0 because there's no acceleration. In the y direction, the only forces we have are the normal force and then the component of gravity, mg cosine theta. Those have to balance each other out as well for the same reason. There's no acceleration in the y direction, no acceleration in the x direction. So what I want to do at this point, so I've done my free body diagram, I've written my equations out symbolically, so those are the first two steps we always want to take. Now I want to plug in as much as I can in terms of equations I know. So I'm going to leave that as mg sine theta. I'm going to put numbers in just a minute. We know the mass, we know g, we know theta. Drag, the equation our author is using to approximate drag, the 1/2 c rho av squared. And then friction. We know kinetic friction is always the coefficient of friction times the normal force. So I'm going to go ahead and jump to plugging in that mg cosine theta for the normal force. So let's see, I think we have enough information. Let's start plugging our numbers in. So m is 75 kilograms, g is 9.8, the incline angle is 17 degrees. They give us a drag coefficient of 1.2 that does not have units. Rho is the density of air. We're using the 1.3 given to us by our author. A, the cross-sectional area is going to be the height times that width. We're approximating the skier to be a rectangle. So 1/2 c rho a v squared. This is specifically going to be the terminal speed. So this v is what we're looking for. Mu, they gave us 0.12. Mass is 75. G is 9.8. Cosine of the 17 degrees. So I'm going to take this term over to the other side, subtract it from the term that's already on the left. I'm going to figure out what that number is. Okay, that leaves me on the left side, if I plugged everything in correctly, 130 point stuff. On the right side, I'm just going to calculate all those numbers, get them multiplied together. So 0.9828 v squared. So dividing by the 0.9828 and taking the square root, I will get to my terminal speed. So let's see, we have two significant figures. So approximately 12 meters per second. So 12 meters per second, that would be a little bit more than 25 miles per hour, which probably isn't all that fast for a skier coming down a hill. This isn't a very steep hill. It would have to probably be pretty long to reach the terminal speed. But again, we're making this assumption, pretending the skier is a rectangle. And that's probably a pretty big rectangle and a big drag coefficient. But again, the process here, our free body diagram, our symbolic equations, that represent F net equals, in this case, 0. So we did need to recognize the term terminal velocity or terminal speed means the skier will not have an acceleration anymore. They've gotten to an acceleration of 0. But hopefully you're seeing the approach is the same. We write out the forces. The new piece is we're accounting for drag here. We will be ignoring drag for most of our problems still. Again, because of the complexity of even approximating it. So the only time you will need to account for drag is if the problem specifically states drag, or if the problem says something about terminal speed. Terminal speed comes because of drag. So those are the two cases, two situations you would look for.